Morning, everyone. We were behind. We're now ahead. So hopefully we can use these minutes productively and constructively, and we can all get what we need from this training school. So my session is environmental modeling. So this is a very large area. We have little time. So what I'm going to focus mainly on is data manipulation, or the representation of data in a responsible way. So environmental modeling, there's a lot of knowns, a lot of unknowns, there's a lot of uncertainty, and there's a lot of variability. And especially as regards nanomaterials in the environment, we have a lot of uncertainty. But we still want to model these situations. We still want to have some idea of what could happen. So we need to use the data we have in the best possible way. We need to identify data gaps that may be there. Through modeling, we can then tell which to prioritize study, prioritize further modeling, or further data collection. So the first part, you can see on the left-hand side, I have a general overview of how the next hour and 3/4 is going to go. Yeah, I can. So over here, you see, first of all, we start with general modeling, the use of data in modeling, how variability is represented, how uncertainty is represented. We then look at its application to nanomaterials. We're going to look at some literature, current literature, involving nanomaterials, and see different problems they've encountered and different areas they've highlighted for further study. We are then possibly going to do a little group work, but that may get cut due to time. And then after that, we're going to look at some modeling software. Now, the modeling software we're going to look at is a spreadsheet-based add-on. And to be honest, it's not ideal. But for 45 minutes, and the 45 minutes we have, we can get a good idea of how to handle data, how to represent this uncertainty, how to represent the variability, and how to responsibly handle different elements of a model. So we're going to look at very quickly different methods of fitting data and then of representing data in models. So as I said, there are better tools out there than model risk, but for a quick overview and a nice visualization of data, so we can visualize the uncertainty, we can visualize variability and how this affects our output, and how our output is not just a single number, but it's a range, it's a probability, it's a confidence interval, different areas like this. So modeling. Modeling can cover a lot of areas: molecular, biological, ecological, hydrological, epidemiology, climate. Lots of different areas modeling can cover. In our case, we're going to look at environmental. So a model is the simplest possible representation of a system that is able to either explain past observations or predict future observations. And it's often used as a substitute for direct measurement and experimentation. So a lot of time it's a lot quicker, or should be a lot quicker than costly and cheaper than costly experimentation or measurement schemes. And so it can be used to help us prioritize study and prioritize where we're going to put our future efforts. And again, when we talk about environmental modeling, there is the environment. So it's everywhere. It's in the urban environments, rural environments. And so this consists of a lot of different elements. And when I say environmental modeling, we're talking about modeling an environment, not the environment. So we're simplifying the system down to a number of elements of interest or a number of elements of influence. So it's a representation of an environment of interest. So you can see here there's some you can see here, sorry, you can get it. From literature, from Gottschalk et al., O'Brien and Cummins, Arvidsson. It's a little difficult to see. Whoops. This is going wrong. Oh yeah, it's a little difficult to see, but these show the different elements of interest in each of the models they produced or they looked at. So, and it's a simplification of the environment you can see at the top of the screen. So, And as I said, the environment you're going to model is defined by your specific research question and the elements you want of interest to you. Your specific research question, what do you want to find out with this model? What is the aim of the model? And this will define the boundaries of your model. So, obviously, in every situation, you have knowns, things that are measurable, things that are easily obtainable data. So it's material characteristics, environmental characteristics. This data is available, this historical data. You can go out and measure it if you want. You can collect it. Also, there's unknowns involved. There's transformation in the environment, aging of the nanomaterials in the environment. And you've decided, is this relevant for your model? Will you include this? Is this within the remit of your model or what it was originally designed for? So, and some of these can also incorporate secondary risks, so absorption of contaminants to the materials. And this produces a secondary risk if it's taken up by an organism, or it then produces a secondary exposure. And you have to think, is this relevant for a model? Is this relevant for a research question? So these are things you have to take into account, knowns, unknowns. And then you have to try and simplify. No model is simple, but it's the simplest possible representation of an environment of interest. So, you want to limit the pathways that you're considering. So all reasonably foreseeable pathways. This may include non-negligible quantities. So, if you have a material that's going to be released to environment, it's going to be released to, let's say, surface water, groundwater, soil, air. Some of these may be released in such negligible quantities, or it's so unlikely that it will be released there that you have to consider, is it worth modeling this straight away? Because a lot of exposure models is to do with risk, and if there's no exposure, there's no risk. So you have to think, is it worth? Which pathways are of interest to us? Which pathways are worth modeling? So, again, we have to think of all reasonably foreseeable scenarios. Reasonably foreseeable. Obviously, there'll be catastrophes and things like this. And you have to think, is this reasonably foreseeable? Is it realistic? Or is it conservative? And when we talk about conservative and realistic, we have to consider both cases. And modeling allows us to do this. We can easily change our input data to consider a conservative case or a realistic case. And so a conservative is where you're thinking, what would happen if this scenario occurred? Just purely hypothetical. The worst case scenario is conservative. So this may help you think, is this within any limits of hazard we found through toxicological or ecological testing? So, and if it doesn't reach that in the worst case scenario, if it doesn't reach limits we found for toxicological, ecological, then you may say, okay, this may be a low priority substance. If the exposure is not likely, or from what we've seen from our conservative case, not realistic, then maybe it's not right. We also have to think, is it realistic? So each scenario we model, is it a scenario that could occur in reality? Are our inputs realistic? Are material characteristics realistic? Environmental characteristics realistic? So we only want to model realistic scenarios as well. So something that could happen in the real world. So that's important. And again, we have to prioritize pathways. And when I talk about realistic, there's very clear examples. For instance, material disposal in Ireland versus Switzerland, for instance. In Ireland, we have no incineration. And we apply our wastewater sludge to agriculture. I think we apply 70-80% of it to agricultural land. In Switzerland, I don't think they apply any sludge to agricultural land. They incinerate it all. So there's two different pathways. So in Ireland, non-negligible pathway, incineration, it doesn't exist. In Switzerland, exposure to soil through wastewater treatment sludge isn't likely to happen because it is regulation in place to stop this happening. And if it's adhered to, then that's a pathway it's a dead end. It's not worth modeling. So, and in any model, there are many assumptions. So, assumptions are a key element in managing uncertainty in modeling processes. So, if we have a lot of unknowns or a lot of uncertainty, we have to make some guesses as to which is the best choice to make. And these are assumptions. So this employs the best available data in logical assumptions, where you consider the available data, choose the best available solution, and consider actions to validate this assumption, and so reduce uncertainty. So we may run our model and find which elements have the most influence on exposure or most influence on a certain behavior. And then we can go back and see how can we reduce the uncertainty associated with this element through more study, through further study, through improved modeling, things like this. And then we can also simplify the exposure process to the pathways and processes of most influence to final exposure or the final behavior. So in the end, the aim is to develop a simplified model. So whittle down through a series of assumptions. So we have a started environment and we think this is not of interest, this is extremely unlikely to happen. And then at the end we have a model that, or a series of assumptions that any logical person would agree with given the available information. So that's important. You have to think, can I justify this? And if you've sent any models for review into papers, you'll find that justification is the key point. They want to see, why did you make this assumption? List all assumptions. Justify them to yourself and reference and justify. So list all assumptions you make at every point in your model. And so when I talk about behavioral hypotheses from available data, there's a paper, Quick et al., 2010, I think, or 11. I have a reference list later. It has summarizes future aquatic nanomaterial modeling challenges very nicely. He looks at the available data and available models and looks at the challenges ahead, what needs to be done, what needs to be improved. So we have assumptions. We also have variability associated with the data available. So variability is effective chance and a function of the system. And this can't be reduced through further study or further measurement. It's just an element of the system, is a characteristic of a certain system or a certain material or environmental characteristic. And so this can't be reduced through further study, but it may be managed within an exposure model through a number of methods. So this can be including data as distributions that describe a factor or function. So we describe this data through its full range. We don't just give a mean value, we don't give a max or a min. We enter data into model through its full range of variability and allow the model to do a number of iterations to represent this fully throughout the model, to give us a range at the end. And again, things that can be variable, climate conditions can be variable, aquatic conditions, nanomaterial or aggregate size can be variable. So within one sample or one exposure, there could be a number of different aggregate sizes or nanomaterial size distributions. So that's the variability. And then we have uncertainty, which is a measure of our lack of knowledge about the parameters of a system. And this is essentially a subjective component. Two people can look at certain facts or certain data and come to a conclusion, this is how certain they are of this or uncertain. It's essentially subjective. So, and through the collection of more data or further study, we can reduce this uncertainty. And so within an exposure model, again, this uncertainty can be managed through a number of methods. So a logical assessment of the information contained in the available data, assumptions and generalizations, where appropriate. So we can generalize and assume our model down to a nice, simple model, but if it's not justified or if it's not appropriate, then it shouldn't be done. And then again, use of appropriate bridging data. So we mightn't have data for nanomaterials, but we have data for, let's say, I don't know, bulk metals, things like this. And perhaps we can use this data with more applied uncertainty to this as bridging data. So it covers the gap, so we are able to model and see the influence of this element on our total exposure, on our total behavior. And then go back and see how can we reduce uncertainty here, prioritize research here. Is it relevant? Is this element relevant? Is further study going to help us understand anything more? Is it worth, in the overall context of final behavior, study, fate? we have to look at this.
How interactive do you want this to be?
Sure, yeah.
Questions or not?
Sorry, yeah.
Just a question.
Yeah, no, I don't mind if I can help. And everyone, I want everyone to help everyone else if people have specific information, because we've got a lot of, intelligent people here who've got a lot of experience. And your experience added up is, a number of orders greater than my experience standing here. So if you have questions and anyone can answer, please, anyone feel free. So.
Because you know, I must have a question. I would not.
I thought so, yeah.
May I ask that?
But please, sure.
Yeah, you talked about distributions, and what's the most common way of getting a distribution? Do you try to approximate it with some analytical function, or you discretize the distribution and calculate for example, exposure and risk for each of the discrete values? That was in your previous slide.
Mm-hmm. Mm-hmm. Each element will have its own distribution.
Say, if I have a histogram or say a Gaussian, what do I do with the Gaussian? Do I calculate the risk for each of the
percentiles for the 5th, the 95th. Well, see, that with modeling, you can run it for 10,000 iterations. And so if you have a distribution, each iteration will sample a different percentile. And if you have enough iterations, you will sample the entire distribution you have. So you will cover all possibilities. And some more likely than others, depending on the distribution you've assigned to this value. So there's parametric and non-parametric. And parametric is where it's model-based. So the distribution is, how can I say, the style of distribution is guided by the mathematics behind this element. So let's say natural organic matter content in water. That's often a log normal distribution in natural waters, as far as I know. So you can represent this as log normal. But if you don't have much data, you can have a uniform distribution from 0 to 1. And if you don't know something, if you don't know anything about a certain element, you can just go from worst case to best case, and it'll sample equally throughout it all. Or you can have a triangular with a maximum, a minimum, and a most likely, and this just samples. So when you've got very little data, or there is no natural distribution that fits to it from literature, you can just put a uniform, a PERT is like for expert opinion, triangular. We'll look at this a little later. But it's talking about iterations, and when I say iterations, we run the model 10,000 times. So we get the full range of all the different variability from all the different elements, sampling from different points at different times. And in the end, we get a representation of what we know, which sometimes isn't very much, but we can work.
Question is rather technical. Say, what's the most common input? Is it just a number or a distribution?
The most common into an environmental model.
Yes.
A distribution, I would say, because it's variable. Climatic conditions vary, aquatic conditions vary, soil conditions vary. Nanomaterial or uncertainty about things is very high. There's no fixed one characteristic for nanomaterial. You can say, this is it, this is the only thing. There's surface coatings, there's lots of different things. Yep. No, that's a good question. Uncertainty. Mm-hmm. So, again, I didn't do a good job of illustrating variability and uncertainty, but we'll look at it later in more detail. So, keeping variability and uncertainty separate in a model is mathematically more correct. So you'll have certain elements that vary, so there's natural variability in these elements, and in certain elements that we're uncertain about. And these can be both represented by distributions, and they can look very similar. And we can use them in a model at the same time. But if you want to go back and then calculate how much of our variability in our end result is due to natural variability of the elements, or how much is due to our uncertainty of the elements, we would have to keep them separate in a model. But mixing them together produces a reasonable estimate of total uncertainty under most conditions. So, representation of data. If I'm going in the right direction here. Yeah. Oh, this might be a little different to your slides because I tinkered with it, but not much. Maybe one slide extra and some little data differences. I think this updated one may be available later through website or something. So, when we talk about representation of data in a model, the accuracy and applicability of environmental models is reliant on the quality and responsible use of available data. So we might have data and lots of it. And let's use this in a responsible way and use it, represent it in an appropriate way, then the result we have is meaningless. So we have to know how to use this data, how to represent it, which distributions can we use which are appropriate for our level of knowledge. And so this data can come from many sources: experimental data, survey data. So this could be expert opinion. And expert opinion can be represented sometimes in models in a qualitative way. Standard monitoring. So it just come from standard monitoring of aquatic conditions or atmospheric conditions. Could be historical data. If we can manipulate this in some way or use it, we can use this. So there are occasions when the observed variability of this data may be applied as a probability distribution in an environmental model. As I said, the observed variability, natural variability within an element of our model. And also we can also, as I said, include expert opinion. So, whoops, can I get this? And so we can use multi-criteria decision analysis. So, and if you talk about multi-criteria decision analysis and nanomaterials, just type in link off and nanomaterials into any research paper, search engine, and you will get a very good overview of how this is used. He's used this to look at regulation. He's used it to look at prioritization of future studies into environmental fate and behavior. So, but we're not going to look at that right now. Again, we have to consider the data quality. We have data. Is it good enough for a model? Is it appropriate? So are characteristics used in past or standard environmental models relevant? So there are a lot of kinetic models out there to do with colloid behavior and environment. And we've got to think, are all the elements they use in these models relevant for nanomaterials? Are they appropriate? And then if they didn't use certain elements or weren't involved, do we have to add extra elements for nanomaterials? Do we need to change these models for nanomaterials? Do we need to represent the data in a different way? So, again, oops. So if you want to look at what elements are of interest for nanomaterials, again, there's lots of literature out there through Novak, Handy, Christian et al. Again, there's a list later of these. And you have to think, is data we have available from experiments, from fate and behavior experiments in the lab, is it relevant for environmental models? Were the characteristics of the materials they used relevant for commercial materials that are going to be released to environment? Were the concentrations they used to produce estimates of aggregation likelihood, were their concentrations realistic, what might be found in the environment? Were the environmental conditions realistic? Did they use organic matter in their studies? If they didn't, then you could say, is the data we have from here, is that applicable to the environmental conditions that we'll find naturally? So, and because from experimental data we've produced in environmental conditions we'll find that we want to model, things can change from concentration that's going to be there, size distribution of the materials, surface area of materials, surface coating, organic matter concentration, lots of things can be different between the two. And how do we represent this in our models? So, and again, when we're talking about different elements of the model and their influence on the end result, or influence on each other, relationships with other elements in the model, we've got to think, is it first order, is it second order relationships? So first order, in the simplest way, it's a constant rate current process, and it's independent of other elements. Second order, you can think it's dependent on other elements. It's a lot more difficult to model, a lot more difficult to include in a model. This can include aggregation rate of materials, For instance, you can say the aggregation rate depends on the number concentration of the materials in a certain environment. But then the number of materials in the environment depends on the aggregation rate. So, again, it's second order, and this needs to be modeled. You could not calculate this. You need to model this because it's a complicated process. And again, we have to think, is our data parametric or non-parametric? I mean, the distribution we're going to fit is parametric if the maths reflect the system being modeled. So, size distribution of nanoparticles in certain material will often be parametric, because depending on the production method of the material, this again may be log normal, it may have different shapes. It's just a natural occurrence of the process. If there's a lot of empirical evidence for a certain distribution, so people have used it before, or there's a lot of evidence to use it, if you have lots of data, and this data is convenient, again, if you have a lot of data, and there's a lot of evidence that this model, this certain distribution fits very nicely to it, then you can use parametric. Non-parametric, if assumption of a specific distribution is not warranted, and it then generally is more conservative, and again, the mathematics behind the distribution you choose the mathematics of the element or the representation of it. Again, it's triangular, it's uniform, it's paired, things like this. We'll look at this again in more detail. Again, we have frequency distributions, probability distributions, uncertainty distributions, which describe different elements of what we know in a model and different things we know about the elements. So, and variability and uncertainty can also be combined, which is, again, difficult to visually represent. But you'll see that, especially when you talk about second order. It can be variable, but also an uncertainty associated with that variability. Again, it's easier to see this a little later. So, for instance, we have to think about different elements, how we're going to represent different elements in a model. So in this case, we're looking at the fate. It's just in a process, because these are nice boxes, they're nice contained processes. We have primary treatment, secondary treatment. The environment is not so nicely contained. Things mix in together, and things go back and forth. It's a mess there. And it's difficult to model this mess. But, for instance, for this short example, we have designated that the concentration of nanofraction contained within the influence is fixed. Obviously, this will be variable. But let's say for this example with fixed, we have a fixed number. Finally, we have a number we can use. And then it can choose its pathway, and this will be variable. So it can choose pathway. This could depend on different environmental conditions. So whether it goes to overflow, if there's a lot of rainfall, certain wastewater treatment processes go into overflow, so they don't go through the treatment system to help deal with the amount of inflow. And then you have your removal efficiencies within these processes. And we have a certain uncertainty associated with this. We're not sure exactly. Different people have measured different things. We have bits of data here and there. We might have a maximum, we might have a minimum, we might have a lot in the middle. So we have to think, how can we represent what bits and pieces of data we have? Do we just take the maximum? Do we just take the minimum? So if we took the minimum, that would be very conservative. The minimum removal efficiency, that's a conservative estimate. And this will give us, if we want a realistic, then you'd have to measure or model all the different elements, the bits of data we have. So, if we want to talk about common modeling errors, and everyone makes these all the time, and sometimes you only realize this later, that you've made this error. It mightn't have a big effect overall, but it does have some effect. And you've got to look out for these things. So, the first is calculating means instead of simulating scenarios. Or even after you simulate a scenario, you just take the mean from that and use it somewhere else in your model to carry on the next part. that mean is just a probability-weighted average of all possible outcomes. It's not the outcome. It's an average of all possible. It mightn't even be realistic. So, the second one is representing an uncertain variable more than once in a model. So, if we have x and 0, 1, and this is what we know about it. It varies naturally. And we have a simple equation. So when I say each iteration, so iteration 1, we sample, we take a value. Iteration 2, we sample, we take a value. 3, we sample, we take a value. And this carries on and on and on, and then gives you a distribution at the end of all possible outcomes. So if we have x here, and we sample here for this value, and apply it here, here, and here. So we have the same element, but we've sampled from two different places because we've used it twice in the model, and the model doesn't know this element is the same. You've represented it twice. So this is unrealistic because this is variability. So what we want to do is have it represented once in a model, and this is used. This one value is used in both cases. So this creates a realistic scenario. This is unrealistic, that the same one value that's variable can have two different values in one scenario. In different scenarios it can have different values, but in one scenario, a single scenario, this cannot have two different values. It's unrealistic. So we have to make sure that every variable element is only represented once in a model for consistency. So, and then 3, we have manipulating probability distributions as if they were fixed numbers. So in this case, we'll take the example of if we have surface area. And we have one case where we're uncertain about the surface area, and one case where we have a variable surface area. So we know we characterize this material, and we know the surface area varies throughout the whole sample. Another case where we don't sure, we have an idea, we're uncertain about this. It could be between this and this. We don't know much about it. So in this case, uncertain. So we just have a uniform from 0 to 1. Because we know nothing about this. It could be from this to this. And it's equal probability of it being at 1 or 0. So if we want to measure then, let's say, concentration by surface area to get surface area exposure. And we take an iteration, and we give a value here, or here, really, and apply this to surface area. This value, for all the material in this concentration, this value is applied to all nanoparticles. And because this is uncertain, this is okay, because each scenario it's applied to each particle, and because this is realistic, and it changes. So, but if we look at the variable case, we might have a long tail here. We're going to go again from 0 to 1, and in the same case, and we take a sample, and again this is applied. Nanoparticles. This is wrong because if it's variable, in this scenario you're saying that all nanoparticles have this surface area, let's say 50 meters squared per gram. But because in this whole scenario, you can't say every single particle has this. If it's natural variability, that's totally unrealistic that every single particle will have this surface area. So if you're talking about variability, you couldn't do this. But because it's uncertain, you can. I hope I can explain this better later. So you have to be careful about how you use these things. So,
if you would have a triangular uncertainty distribution, then apply this to what you say about the variable, then also you cannot just choose one.
well, no, in that case, you can, because in the whole scenario, because you're not saying that, in this case, you know this is true, that it's variable. And if you take particle A, B, C, D, they'll have different. But if it's uncertain, we don't know, you can say they all have this. You could all have, 50 instead of 60. You wouldn't then, it would be wrong actually to give a different to each one because you don't know. You want to look at each case if it's 50, if it's 60, if it's 70. But because we know this is the natural variability, we have to be true to the representation of the data. And for each particle, it's got to have a different sampling point. So in that case. Yep.
Would you recommend minimum actions to validate the model? So can you give some ideas what should be validated?
Which elements, or how, once you have your model, how to then?
Yeah, I think it's usually you have the input data, and your model is usually as good as the input data are available. If you have not so many, you have to live with a lot of uncertainties. Yeah, I think then the output can have a large variety. So
yeah.
So what would you recommend, or also if you do such errors, to prevent this, to validate some minimum requirements for your validation of the model?
Yeah, when there's so many uncertainties, so much uncertainty, so that you can only validate each element of your model. You can try and justify, and then go back, and the elements that are have a lot of influence on your final thing, then try and validate these, try and maybe then do some studies to see what is the removal efficiency, what is the aggregation rate, what is the dissolution rate, what is it in reality. Yeah, when there's so much uncertainty, it's difficult to validate an entire model, but you can validate in elements that have a lot of influence on it. And yeah, validation usually requires data at some point. You need to measure something at somewhere, and until we start measuring regularly in the environment, nanomaterials, then it's going to be difficult to say one model is better than another.
This is precisely the point about modeling, is that it helps us to identify what are the crucial information that we need in order to narrow down the uncertainty. So don't take the model always as an end product that is known. It is something that is in your toolbox. It allows you to quantify your thinking, your understanding about the process. And if there's so much uncertainty in the model, that is because there's so much uncertainty in our knowledge. And we just try to quantify our thinking by putting distribution and so on into the model. But what it really does is that it says, this part of the model, I don't know so much. This part, I know more. And if I put all of my knowledge and my lack of knowledge together, this is what I get at the end of the day. But what it tells you is the end product that you get, which is fuzzy. It can tell you 60% of my fuzziness in the end product is due to this bit of one bit of the model that I don't understand. You see what I'm saying? Because the model consists of 10 parts, for example.
I agree completely, but I think sometimes, or when I read these modeling papers, I often miss that the uncertainties are hidden. So you have a fixed number at the end, and you think, oh, so I can assess how much it is. But usually you have 100, 200% uncertainty. So this is not always given.
I agree, and I hope this is the aim. One of the aim of the school is to clarify some of the wrong perception about the model. You think that modeling, in some case it works. In some processes in which you understand everything and you can explain everything, that's fine. But in most of the case, like in a very complicated system like the spreading of nanoparticles in the environment, there are bound to be a lot of subcompartments in your model that you don't know so well. And what it does here is it helps you that you put all these things together, you can identify which bit actually drive the final uncertainty. And I think that's the point that you're trying to make, and I want to emphasize on
Yep. Exactly. And then we got to think which elements, and if we have a massive uncertainty about a certain element of a model, a certain compartment, we can assume, so a black box approach. Something goes in, something's come out. We're going to ignore what happens in the middle, but we have some idea it's going to be this order of magnitude. And when there's a lot of uncertainty in a model, especially when you read papers about, exposure concentrations, things like this, at a certain point, you don't look at the numbers, just look at the order of magnitude, because that's all that matters. The numbers are meaningless, like it could be, so it's order of magnitudes we're talking about. And we'll see later how Quick et al. Gave some order of magnitudes for different dissolution rates, for advection rates, different things like this. So we'll look at this later, but it's just about focusing on the elements of the model that drive the uncertainty, uncertainty. So, again, when we talk about simulation, we should calculate where possible. As I said, we can calculate, if you have first order rates, the constant, we can calculate these things. But again, more complex programs, second order, where different elements interact with each other and have an influence on their outcome, we need to simulate these things. The level of accuracy depends on iterations. Again, iteration is the number of times you run a model. And often we'll run a model either for a fixed number of times, or we run the model for as many number of times it takes to reach a certain state, a state of interest. And again, often there'll be a mix of the two. We calculate the straightforward parts, simulate the rest. And again, some that are popularly used, Monte Carlo simulation. So it's random generation of values from probability distributions. As I talked about here, we have probability distribution, and it will randomly generate values from this distribution. Different sampling methods, I won't go into that now. And then Markov chain Monte Carlo. Markov chain is a very interesting tool, because it allows individuals or elements of model to randomly to change states in the environment. So nanoparticles may be free, floating around in water, let's say. Then they may aggregate. They may disaggregate then as well. They may move from one state back to the other. They may aggregate and then settle or sediment. And then they may again be resuspended, so move from this state back to suspended in aggregation state. They may dissolve. That's an end state. They may degrade. They may leave the system that you're in. They may advect. They may leave the system that you're interested in. So they can change states back and forth. So it's not a one-way process. They change states back and forward. And again, through Markov chain Monte Carlo, we look at this. And we look at a paper later which considers this method, considers this. Again, if we interpret the results, we can run for different iterations. So again, it's sampling at different points. So take sample here, here, and you keep going until, for a fixed number, 1,000, 10,000, 100,000, or until it reaches a certain state. And then we get results. So here you can see a result in a table, for instance. You can see a result in a histogram and a result in a box plot. This is the same data, represented in different ways, and allows us to visualize it in different ways. So again, here you have a histogram. So this is, again, this is driven. Oh. So let's say we have a constant. If we have a concentration here, let's say this is concentration in water, and this is variable. It varies. And let's say this is surface area, and we're uncertain. An uncertainty about this. And in the end, we get a result like this, surface area concentration in water or air or wherever. And this output is driven by the variability and the uncertainty we have in our inputs. You can see here, this is 10th percentile, 90th percentile. So in 10% of cases, it'll be above this. So then we have a confidence interval. That's an 80% confidence interval. So we could be 80% confident that it will be between these two values, or output. Here, we have 98% confidence interval between one. We can be 98% sure it'll be between this value and this value. And here again, we've got a 50% confidence interval. We can be 50% sure it'll be between this value and this value, and then we have a mean. But as I said, a mean is just a probability-weighted average of all the outcomes, of all the possibilities. We can then see how the different elements influence the model. So the two inputs, concentration, surface area, and how much influence they have on our model. So this is the relative influence of surface area and concentration on our output. It's very simple. Two elements multiplied together to get another. We can see how the inherent variability or uncertainty associated with that drives the output. And again, when I talk about applying these results, so we do all this modeling, and we got to think, where is it applied? What use is it to us? So again, for one instance, we use in risk assessment. So in risk assessment, so to assess a new pollutant or new material, we have to think about both the exposure and the hazard. And sometimes, if we model the potential exposure or future exposure, if we find there's no exposure or very low exposure, there's no risk. If we find there's no hazard, there's no risk. But modeling, again, may be quicker, may be cheaper than doing the ecotoxicological testing. So it can be used for risk assessment. And again, used in risk management then. Once there's risk assessment, we can use this risk management. So, to help guide regulation. And then another element is important is the definition again. I've heard if you're involved in any kind of nano testing, regulation, anything to nanomaterials, the definition is important. And so you've got to think the nano fraction of materials are already regulated. So this nano tail of a material, this may be the size distribution of a material. It's more likely to be out here. But this is this small tail, which might be very low on a mass basis, on a surface area basis, on a number concentration basis. This would be very significant. So, but that's for probably a different, not for the modeling school, but it's an element to take into account. You also think about risk-benefit analysis. So, what's the benefit of employing this technology versus the potential risks, and relative risks to other alternatives to this, using this material or this product, this process, and its relative risk to other traditional pollutants that we use on a regular basis. So, and again, as mentioned, it's used to help guide future research, to identify areas of significant uncertainty, and then guide future research. This could be future modeling, could be future monitoring, testing, experimentation. So, now we're going to look a little bit at its application to engineered nanomaterials. So we looked at different little elements here and there, but this is, we're going to look at some literature which addresses this. So then, and have a quick look at it. Then you can go back yourselves and see what is of use to you, what methods do they use, or what conclusions do they come to that you can apply directly in your own modeling. So that's 22. So we have to think, what is released? This can be, what form is it released in? So we have titanium, silver, iron oxide, lots of different materials. But what is it? How is it released? What form is it released in? Like in a product, it could be surface bound, it could be suspended in liquid or solid, it could be free, little particles doing their own thing. So it can be held in many different forms. And the status of this can change during the life cycle. It will change through degradation, through aging. Something that was initially highly aggregated will disaggregate. Something that was initially surface bound onto something will become free. It will age, it will transform. It'll become associated with other materials, organic matter, associated with other potential pollutants. For instance, a paper years ago, so that arsenic sorbed to TiO2, and then this enables the uptake of arsenic by trout, for instance. We've got to think, but again, these are secondary risks associated with nanomaterials. Are they relevant for our model? Should we include this in our model? Is it relevant? Will this get out of all control then, if we don't? But we should acknowledge it, I think, that this is a potential problem. There's also nanomaterials already in present environment. These could be organic, inorganic. They could be actual, nanomaterials. It's been shown recently that macroscale objects can represent an incidental source of nanomaterials in the environment. I think silver nanoparticles, not just ions, were actually formed in the environment. There's a paper here if you want to look further into that. So again, we want to define the model environment. What is a specific research question? What do we want to find out? What outputs do we want? What are inputs? What are the outputs? What do we want to find out? What are the parameters of influence? Which engineered nanomaterial, E&M, engineered nanomaterial, we talk about particles, talk about aggregates, lots of things. Which ones are of influence? Which environmental characteristics are of influence? Are they quantitative? Are they measurable? Do we have data for this? Dependencies. So which elements depend on other elements? So again, you have to represent this in your model. Which are influenced by other elements? So again, a second order, it's dynamic, things change a lot. So what data do we need? Is it relevant to the environment or nanomaterial life cycle stage of interest? The data we have, but is it relevant? Does it involve the material we're looking at, the material that's used in commercial products, the material that's released to environment and then transformed? How is it relevant all the way through the life cycle? Do you have to change how this data influences your product because your product has changed, or I mean your material has changed?
Could you again, what is the meaning carbon nanotubes should be shaken, not stored?
It was a quote from this award ceremony, the IG Nobel. So it's for outrageous research, something like this. But they also had a section, I heard, where there was a scientist from the US who had to explain environmental ecotoxicology in 4 minutes to lay people, to people who had no previous knowledge. And so she then had to summarize everything she said into 7 words. And so this is what I'm talking about. Is the data relevant? So testing was done with carbon nanotubes to see how they aggregate or disaggregate, how they sediment, how they settle in a sample. But how are these particles stored? Were they treated with anything? Is it realistic for our environmental conditions? So they may have come up with a certain theory or a rate constant for this. But is it relevant for the environment? Is how they were handled, how they were used, relevant for our environmental conditions? We've got to think, we have data, is it relevant? So again, we have our model equations. We may have a great framework. We may have defined relationships and processes. We just need data, which is sometimes the hard part. So populating these model equations. So once we've defined a framework, defined the relationships within the framework, we have to populate this. And so we have to look at the quantitative influence of certain elements, qualitative. We can make assumptions and say something is not relevant, or we can swap this assumption for a distribution to say, okay, we know we know this much about it. We're going to put in this data we know. We might have no data for a certain element, for a certain key point of our model. It doesn't mean we should stop there. We can apply bridging data, maybe from another material. That's appropriate. Again, that's very subjective, but if it's appropriate. And again, if you do this, you need, whenever you model, all your assumptions, state all your assumptions you make, and try and justify these assumptions as well. We can apply a worst case precautionary principle scenario. So we say, okay, at worst case, all of it goes through wastewater treatment. The worst case, none of it sediments to the bottom, and none of it aggregates, things like this. We can look at the worst case scenario. Even if we have no data, we can still, and then go back and see how much does this influence our end result. And if it's high influence, and there's a lot of uncertainty, we need to look further into this. So, Quick et al., 2011, mentioned a few different models and frameworks that describe the fate and distribution of nanomaterials. And some of these incorporate classical knowledge of colloid science. So they try and populate existing kinetic equations with nano-specific data. And then others applied principles used from chemical fate modeling and material flow analysis. So the flow from one compartment to the other and how likely this is. What range is this going to be in? And many of these model frameworks, while useful now, they definitely are. They give us an order of magnitude estimate of what kind of exposures we're going to be exposed to. They may prove very valuable once more data becomes available to populate these probabilistic submodels. So we need some rate constants. We need some first order, second order rate constants to populate these models so we can get a better idea, reduce the uncertainty. So, colloid is just a substance dispersed through another substance, through the microscopic scale. So there's inorganic colloids, so clays, silicates, organic, so humic acids, things like this. So, but from these classical colloid kinetic equations, a number of particle-specific fate equations need to be included to ensure nano-relevance, to ensure they are relevant for nanomaterials. So, among these are sedimentation, agglomeration, dissolution, all dynamic non-equilibrium processes. So, for instance, dissolution depends on the mass surface area balance, but then the mass surface area balance depends on how much is dissolved, especially at nanoscale. So, again, that's a dynamic that's non-equilibrium. Although this may be simplified or assumed to be first order for modeling sake, and then we can go back and look at how this affects. So, as I said, the main challenge is to use the quantitative knowledge of these processes to turn current models fit for nano, as I quick mentioned. So that models we have, which are very valuable and developed through many years and improved on, these are in some cases applicable. We've got to say, but are they fit for nanomaterials? Are they fit for nanoparticles? Are they appropriate? Can current water quality models simply be upgraded with nano-specific process descriptions? So if the nanomaterial water column transport can be described sufficiently well by first order kinetics, we just need to quantify these first order rate constants. Now, they're not all first order, but if it can be described sufficiently well, close to first order or negligible difference, then we just need these rate constants, which is where experimentation can come in. So for instance, quick look at sedimentation. So, interparticle collision and aggregation, and then aggregation, so they collide, and then the sticking efficiency, or the collision efficiency, how likely it is they stay together, is second order in nature. It's reliant on number concentration, and number concentration is reliant on the aggregation. So, second order in nature. So, you're talking about modeling. So, but Quick et al. Found that this tends to reduce to pseudo first order as the amount of collision capacity in natural waters is expected to remain approximately constant throughout the removal process. So, they suggest that we just assume a first order rate constant, a single rate constant we can use throughout this. So it's first order, a single rate constant. For dissolution, again, as I said, surface area is dissolution is reliant on surface area to mass ratio, but the surface area to mass ratio changes once it dissolves. So you're, again, second order. But again, in the absence of more adequate data, Quick et al. Suggests that using first order kinetics for dissolution of nanomaterials is acceptable. But this knowledge gap needs to be filled before dissolution can be modeled adequately. So again, more experimentation is needed there. But they find that you can still model, even though you don't have a suitable rate constant, second order rate constant. You can use first order, still model. You still get a result. But you have uncertainty associated with this. And formulated in this way, you can see here, nice aquatic environment where you have input in, you have a surface water concentration. I keep doing that. And there's different processes represented here. You have aggregation, absorption to other materials, dissolution, sedimentation, advection. So, although the sedimentation probably can go both ways. And you can see over here, total rate constant is made up from all these different advection, volatilization, although for nanomaterials this isn't really applicable. Degradation, sedimentation, dissolution. So, formulated in this way, the challenge of modeling is placed entirely in assigning values to the various rate constants. It's just populating this equation, populating it with data, these rate constants that we need. A weakness of this is that a new removal rate needs to be measured for each individual nanomaterial. And an advantage is that it provides one single approach to modeling of conventional chemical subjects and nanomaterials. So we have a model that describes the process. But do we have data to populate this model? Is it right to assume that these are first order rate constants describe these processes? Or do we need to look further into this? So this is important. Arvidsson et al. Looked at colloid chemistry kinetic equations, describe particle agglomeration and sedimentation. So, and in attempting to populate these equations, they found a number of data gaps associated with nanomaterials, such as disaggregation rates, collision efficiency, so when particles collide, how likely they are to stick to each other. So collision efficiency. And so in their model, they just went 0 to 1, so not at all to 1, and looked at the most extreme cases. Again, this needs to be brought down into some order of magnitude so we have some idea of how much this affects overall. So they found that the inflow of nanoparticles in the water compartment has a significant impact on the model, and collision efficiency, which is affected then by natural organic matter, so absorbing tour particles, was shown to greatly affect model output. And now we've got a more probabilistic model method, so flowing between compartments. and the interaction of different compartments. So instead of looking at the kinetic equations, so the actual how the specific behaviors, the probability of it moving from compartment to compartment. So this was carried out in OR, which is an application of the S+ language. So an open source software with different statistical methods and tools in it, which makes it very powerful. So it simplifies many statistical computations. So you can have very complex models and run them for a number of iterations to get some results.
What's the PDC stand for?
Predicted environmental predicted environmental concentration.
What's an input to this model?
Sorry?
What?
Oh, input.
Yeah.
There was a previous paper by Muller and Novak where they looked at mass flow. They looked at all the so they input titanium dioxide data. So they looked at how much was produced in Switzerland, its likely output to soil, air, water. And so they took, its likelihood to go in these different directions. So they put it from this initial state and then went back and adjusted the model to see if it described it sufficiently or not, or if it described realistic scenarios. So input data, again, some of it was assumed and some was measurable. So they looked at overall production rates of materials and then looked at the likelihood of this to be released from a product or process. And then looked at the probability of it moving from wastewater into surface water onto soil, different things like this. Surface water to groundwater, into air, and then air to soil to water.
You need some transition rates.
Oh, yeah, it needs some rates, some probability rates. If you look at the paper itself, it goes into a lot more detail. I have again, this is their system boundary. So where are we over here? I'll use it nice. So import into the system, so through production, manufacturing, consumption. And then this moves to incineration, sewage treatment, so probabilities of it moving from these areas. Again, down here, so you go to surface water, discounts sediment, likelihood of it sedimenting, likelihood of it resuspending, leaching from soil to water, and then they, again, got likelihoods of it moving around and where it's going to its fate within these processes. So it's more probabilistic. And again, they use Markov chain where it moves from one state to another state. So from free to aggregated to sediment, back to free, to dissolution, to leaving the system, and the probabilities of it doing these things. And then when it gets to a steady state at the end, through inputs and outputs from the system they looked at. So again, this is a visual representation of their system. So that we'll not do. And is a few references. Again, there's more in there. I have the names and years. There's the names and year and nano something, and you'll get the papers. So I think that should be in your list. So, interactive session. We'll see how this goes. So basically, modeling software describes as software that allows us to represent the data at hand and recreate desired scenarios. So to run models, this can be, as I said, financial models, climate models, it can be environmental models, it can be biological, molecular models. Again, you need input, you need to represent the system you're interested in, have boundaries, and to define the relationships within this system. So it can be done through spreadsheets, so through Excel. And there are a number of add-ons, statistical programs and packages. So as I said, within this talk, I've focused on representation of data and how to represent uncertain data. And so representing this uncertain data, and when you talk about uncertainty in data, it's nanomaterials, because we're uncertain in a lot of things, there's a lot of variability. So these statistical programs can be at risk, crystal ball, model risk. Advantages is that they're easy to pick up. They're very visual, very tactile, so you can really see when you change something, its impact. And it's good for demonstrating the handling of variable or uncertain data. But it scales badly and is limited to 2 or 3 dimensions. So I would say 2 is the limit before it gets out of hand and before different modeling environments are better. So, cannot easily handle the modeling of dynamic systems. And so multi-dimensional problems are more suited, so environmental modeling, are more suited to modeling environments such as C++. MATLAB or Mathematica and Maple have powerful built-in modeling capabilities that can handle many dimensions. So these are very specific. But for this, I just focused on the handling of data. And through this, you can represent the model system. And so this equation here is from Quick et al. We looked at earlier. And so it describes surface water concentration. And so it shows the relationship between different variables. So all of these are directly influence the steady state surface water concentration. And we can visualize this very easily with influence diagram. But then you also have to think that other elements influence each other as well. And sometimes in both ways. So then you get to a next level of interaction, so a lower level of interaction. It's visual, these influence diagrams, but the mathematics and data behind the model are hard to get to. Event trees. So it describes a sequence of probabilistic events, their probabilities and impacts. So these event trees are built out of nodes and arcs. So each node, so let's surface water is one node, sediments another, groundwater another, and arcs that represent the relationship between these different elements and that represent how they influence each other. So the mathematics to combine the probabilities is relatively simple, and a diagram helps ensure the necessary discipline. So models can get out of control. A diagram like this, where you measure where everything is going, you have everything under control. You don't lose any data, you don't lose any elements in a model. They're all there. And then discrete event simulation. You can read about this. It's mostly there, what I mentioned. So, if we talk about data manipulation, we can apply distributions to data. We can apply a correlation to 2 variables. So again, 2 variables. They might both be variable within the model, but they vary together. There is some connection between these, a correlation between them. So you don't want completely random sampling from each one. So here to here, and let's say pH and calcium concentration of waters is off. There is a correlation there. You can see. So you can do rank order correlation, copulas, look at the correlation coefficient, and guidelines for this. Then we're going to look at material flow analysis. Very simple. So going back to this here, I just took that and thought, what can we do in half an hour, 45 minutes? We can look at this. First order rates. So again, there's no second order rates here. We looked at just first order rates. With defined parameters, defined influences, we're going to look at handling input data, uncertainty, variability, and interpreting the results from it. So you have an input, advection, so leaving the boundary, the system we're looking at, sedimentation, degradation, and then a concentration in sediment and surface water. Again, we're not looking at resuspension. We're not looking, very simplified, stripped down. Oh, so I'll just change computer. So I don't know if you all have model risk, or if you just want to watch, or just try and just put in some values and see how we write them.
If you don't have the software, we can provide it.
Sorry?
If they don't have the software yet, we have it downstairs
Okay.
on a stick, so who still needs the software? I'm just going to get it.
It's not so. This is just really visualizing that and see how we. So you can put all this in and get results, but then how do you read the results? What do you take from these results? What's important? So let's say, for instance, we're looking at removal efficiency of materials in a certain process. And reference 1 says there's 99. They measured it, there's 99% removal efficiency. Reference 2 says 97%. 3, 20%. 4 says there's 96, 5, 94, 6, 97, and 7, 92. 8, and it says 80. So you've got lots of different opinions, either measured, or it could be expert opinions, it could be actual measured data. And we think, what do we take from this? If we were looking at a worst case scenario, you could just take 20% and say there's only 20% removal. The rest leaves the process somewhere else. You could take an average of them all and use one value, but why not try and represent all this data in some way? So, and use this. And so then your model can randomly sample from all of them, or even the bits in between them, but with a frequency that's associated with the data we have. So you can see it's weighted towards the high 90s, 95 to 99. So the removal efficiency from either from single values measured or from expert opinion.
So, what exactly do you mean by removal efficiency?
This could be any process. So it could be, let's say,
So it's about removal of nanoparticles from where to?
let's say wastewater treatment, a wastewater treatment process. You have influent going into the plant and effluent at the end. You measure the influent, the effluent. People do this and they say, oh, 99% is removed. Someone else might measure.
99% stays in the plant.
It stays in the plant. Well, it then goes somewhere else. You have to model, yeah. So it could go to sludge. And if it's in Ireland, that sludge will go to soil. If it's in Switzerland, that will get incinerated. And so you've got to think, where is it going to go then? So.
May I ask a more practical question?
Yep.
How do I enter the model?
Oh, sorry. Yeah. You can either open Excel and then just open model risk.
Yeah.
On a ribbon up here, there's a model risk.
I open
Sorry.
that and
Is it there?
what's next? Yeah.
So this is the different tools we have, model risk to add-on tools, statistical tools. So I'll show you. So here we have some data. So
I just create a spreadsheet, or how do I enter the model?
oh yeah, this is just a spreadsheet. This is normal Excel spreadsheet. And so we just enter this data, 99, 97 to just in a row. And then we can think about different models we can fit to this. So if we look at the bottom three maybe. So if we think we can use a uniform, which assumes, so uniform means we have a distribution between 2 points, and we sample evenly throughout this distribution. Each element has an equal likelihood. So we're saying we know a maximum, we know a minimum, we don't know anything in between. And so we're going to sample from this. And in this case, it's called, you put in Vaux's uniform. And for this, we just took the minimum and the maximum. So Vaux's uniform, you put in the minimum, you put in the maximum, okay? And this gives you a distribution that you can sample from. We can visualize this here.
Should we just copy the data to our first?
Oh yeah, this, yeah, sorry.
It's a little bit as if we're looking straight at the results. Shouldn't we go through the process how you use this model?
Yeah, this is no, this is just representing this input, this uniform input.
So 1.1 is input.
Which
Fitting distribution of data uncertainty. This is the input. That's how we start.
yes, yeah. So we have this data, and we want how do we represent this in our model? So wait, I'll go back one. Oops. So for instance, we look at uniform again. We have min, max, and it's equal likelihood. So this is the density, so probability density. Equal likelihood. So each iteration, so one scenario, it will take this, I1, another one will I2, this I3 might be here, IN. So it will sample as equal probability that will sample and all of these here. And for this, you just need a min and a max. Yeah, 45 minutes. So that's uniform. And then once you type that in, you can say view function, and you can see how it looks. So it's equal, as I said, it's equal probability throughout it all. An X there. We can also say a triangle. And for this, you just say Vaux's triangle. And for a triangle, you have a min, most likely, and a max. And again, this is your probability distribution. Density, sorry. And so the most likely, there's more, the probability is higher that it will sample from here from your most likely. So it's a different shape distribution, and so it's weighted around the most likely, but it takes into account your max and your min, so it will sample from here some extreme values. And so, in this case, I took the minimum that was referenced, the maximum, and then I just took 97 was kind of a mode, so I took that as most likely. But you could take an average if you wanted. But the average, I took the average of this, and it was about 0.84, and it didn't think it felt it was weighted heavily enough towards what the data shows. So, and again, visualization of data is important. So here, you can see here, you have your min 0.2, max 0.99, and a most likely. And this will sample at different points, but most likely up to this end here, because you told it to do this. So let's say we look at a uniform and a triangle. With uniform triangle. And
Could you explain, I understand that O2 is the minimum,
yes,
O99 the maximum, and why did you pick?
the 97.
Because you have these two terms, is that not like?
I just took a mode for that. Yeah, you look at the data just for, as I said, I took an average of them all, but this was weighted towards 0.84 as an average. And I didn't felt that was a most likely. Looking at this data here, it's weighted more towards the higher. So again, visualization and how comfortable you feel about how this represents your data is important as well.
So first you have
Yeah.
you call the specific function.
Sorry?
When you call this specific function,
Mm-hmm.
entirely, for example, you have first to do some statistical manipulation of the data to find which is the most likely.
You could do, yeah. This is a very
Because
simplified,
you have only eight values, but
Yeah.
if you have
many values.
yeah,
Yeah, you can then. If you had a lot more values, then maybe an average would be a good,
an average
most likely.
Or a medium.
Or median, exactly. Yeah, this median mode. So again, what?
Was most likely.
Yep. There's again many different ways, and whatever you feel represents your data best. So, let's say we then have an influent concentration. Okay. I took this as a normal distribution, Bose normal. So I'm going to get rid of this for now. Sorry, a bit ahead of myself. Bose normal at 0.5, which milligrams per meter cubed, just for any value, and 0.1 as a distribution, so like a 20% uncertainty. So, and then, so we can actually, I'm just going to get rid of this here as well, just to make it easier. That's putting boundary on it. That's another element. So, we have input. You can say that this is variable. It varies. Its mean is at 0.5 milligrams per meter cubed, and we have a variability around it. So we can look at this function. Sorry. View function. And that's it here. So this is how it varies. So you've got your mean, and then varies around here. And this is a cumulative graph. So and then let's say, so we're going to look at these two here. Okay? Uniform and triangle. And so this removal efficiency, and then we're going to, the influent, have a removal efficiency that's represented by uncertainty distribution. So, and again, that's 3 and 4. So, again, as you can see here, this is just influent multiplied by the removal efficiency. Or, so we want the effluent, so it's 1 minus the removal efficiency. For uniform, oh, damn it.
Excuse me?
Yeah.
So each time you're entering a new, it keeps changing.
Yes,
the number.
sorry.
So,
That's because it's sampling. These are all distributions.
so each time you're
It's taking
doing
a
new
different sample.
iteration. Okay.
Yeah, so it keeps, yeah, sorry, good point. So let's say I'm going to go, where am I? Oops, that's not what I wanted. So, for instance, if I press F9, you can see it changes, it samples a different value from these distributions that we defined. So for each time I press this is one scenario, another scenario, another scenario, another scenario. And then at the end, we do this like 10,000 times you can. You can do it 100 times, 1,000, 10,000, a million if you want it, depending how complex your model is. And then you get an overview of all these possible scenarios. Remember, these scenarios have to be realistic, so the input you have has to represent a realistic environmental scenario. So if this here, fit 3 represents a uniform distribution multiplied by the influence, so removal efficiency, to get an output. This here represents triangle by uniform. So I'm just going to, so here. If we want to, and we want to look at this, we're interested in this value, okay? So we're going to go to output. So we're going to put effluent uniform removal. Oh, doesn't matter. That's an output. We want to look at the distribution we defined earlier. We're going to put that as an input, so we're interested in the influence of this. So, influence. And we're also interested in the original concentration in the influent. And so we're going to put this as an input. So you can see here how many samples, how many times you want to, we'll do 1,000. And we're going to run this. Okay? It's very simple, so it's a very quick. So,
sorry, can you tell me again, how can I use the table as an input to fit with the
this here?
So, yeah, I entered the column of data, so...
Yeah. So then we want to put a distribution to this. So here we looked at the data and applied a uniform distribution to it with a minimum.
How do I apply?
Can you just walk through the steps?
Okay. Yep. So here I'm going to create another one here. So I just, and it gives me lots of different equation possibilities here. Votes uniform. And so then I put in my minimum, 99, and maximum. And if I press F9, this samples from this distribution, uniform distribution. And you can see there's a difference between this here, original. They're the same equation, but they're different. They're different. They're separate. They're sampling from different points because they're separate.
How I choose to what set of data apply that, or you simply you just look up the minimum, the maximum value. So
for a uniform.
That really fits this distribution, but you just.
It doesn't. You're right.
Okay.
It doesn't. Yeah, we don't have much time here. But that's one option. Then we can.
Is it possible at all
to fit?
Yes.
Oh yes, it is. So. So insert. Okay. Well, this isn't activated in this, but there is a fit version. So it will give you. You can put the data in, then say to fit, and it will give you a few options of different kinds, and you can decide goodness of fit to this data. But again, you have to think: is it realistic? Is there any reason for using this distribution? So in this case, we're just looking at it and applying your own distributions, but you can also fit distributions to data, especially if you have a lot of data. You can also fit distributions to this. So we have a uniform and a triangle. And so we're going to look at the influence of those two here. So effluent, uniform, and triangle. Oops. Uniform removal. just so we can identify it in the output. So we have those input. These are inputs we're looking at. Uniform distribution for removal. I'm going to put this as an output as well. Put this as an input. So, and we're looking at these two outputs. So I'm going to run this. That's my previous results. It's not interesting right now. So, we're going to look at a histogram of that. And so with a uniform distribution, you get a very strange distribution because it's sampling equally from right across. And so you can see here, oh no, that's, sorry, no. Output, sorry, I'm just going to go back here. Sorry. Uniform removal, we can see this is the output. So it's sampling from 20% removal to 99% removal. For all these different scenarios, so each time we redo it, it takes a different scenario. And in the end, this is the overall effluent concentration we can expect. And this is our confidence interval from 90% to 10%. We're 80% confident that it'll be within this range, given what we've looked at. So we're going to unselect those. We're going to look at for triangular removal. And for triangular, it looks a little different. It's more concentrated around the most likely. So here we had it looks a little bit like the distribution we had, but again slightly different because our influent concentration was a normal distribution, so some in the middle and tails at the end. So and this is what's called a tornado distribution. So this tells you the influence of the two elements. So so this is the influence of removal efficiency, and then the initial concentration in the effluent. Initial concentration in the influent, and then removal efficiency. And this tells you the relative influence on the final concentration in the effluent. So this has a negative effect. So the higher the removal efficiency, the less concentrations are in effluent. And then the distribution of the influent concentration, the higher that is, the higher there is in the effluent. And so for our case, you can see the initial concentration in the influent has a far higher influence on final effluent concentration than removal efficiency. So that's one example, which didn't go smoothly as I hoped. And so I'm now going to look at correlations. So again, two elements are variable. So we have, let's say, two elements. They both vary, but there is some kind of link between the two. There's a correlation between the two. And you want to represent this in your model. You don't want just completely random sampling, because they have to correlate. There have to be realistic scenarios. So again, if your pH is high, it's unlikely, in Irish conditions anyhow, from sampling that's been done, that your calcium concentration will be low. So they have to correlate in some way. It can't be completely random. They have to correlate. So, in this case, we have, again, some data, some very sparse data about pH calcium concentrations. And I've applied two distributions to this. So, I've done very simply here, I have applied a uniform distribution to this. I took the minimum and maximum in this case. And again, for the pH, I took both uniform, a minimum, and a maximum. I don't mind about these things just yet. But then I wanted to correlate the two. So I have this value here, correlation coefficient, 0.9543. That helps. So they should correlate to this effect, to this much. So I can, one way is with copula, so bivariate copula. There's two elements to this. And so this gives you different types of copula. So it's not totally random. There is some variability in how they're selected. So when this is selecting from the 10th percentile of a distribution, say 10th percentile, if it's complete correlation, these will both sample from the same percentile each time. They can be different types of, this can be uniform, this can be triangle, they can be different scales, but they will sample from similar points if there's complete correlation. And as correlation goes down, so the normal correlation, so it's more in the middle, there's a bit more variability. So, and the covariance, if it's 1, they correlate exactly. So, when this is sampling from the 90th percentile, this also samples from the 90th percentile. When this samples from the 20th, this also samples from the 20th. So the correlation in how they take this data away. And as the correlation coefficient reduces, there's more variability, more 0.1, down to it looks completely random how they correlate. So, and then there's also, going quickly into it, there's also different styles. So in this case, if there's more correlation at the lower end of your data, so as you can see here, there is at the lower values of pH, there's a bit more correlation with lower values of Ca2. But as I get to higher values of pH, you see there's a little more variability between the two. So for this case, I'm going to colorate. And so lower there's more coloration, and higher there's a bit more variability. I'm going to select the two values we want to put in. Oops, sorry. I've got to change this slightly. Doesn't like that. Yeah, I know. So, coloration. This is the style I want. I'm going to take this distribution. And I want to colorate it to this distribution here. So, and this is how it's going to sample between the two. Okay, sorry. So, and I want to show the sampling percentiles. So you can see here, when this here is sampling from the 68th percentile, this is sampling from the 60th. In the next case, when this is sampling from the 58th, this is sampling from the 83rd. In the next case, when this is sampling from the 87th, sampling from the 60th, 82nd, 91st. So there is some correlation. So there's not completely random sampling. They are in some way connected. Still random, but it does give you a bit more realistic situation there. So correlation is important. You've got to think, how much did it correlate? Which elements in your model are codependent on each other? So, in that case, we have that. I'm sorry about this. In my head, I thought this would go a lot smoother. And when you've worked with something for 5 years, I've actually worked with at risk. So model risk is something new because it's open, it's free, standard version for everyone. But I only hope it shows you how you can visualize distributions. So let's say we have Bose uniform. This one here. Again, you can see it's a uniform distribution. You see a Perth distribution here. So it's slightly more, it's not like triangular, it's more for expert opinion. Oops, sorry, where you have ideas of a mix, a max, a min, and a most likely. So it's good for visualization. And then, as I said, your outputs. No. Simulate all this again. So, now. So you can see here, again, this is our output. It's not a single value, it's a range. And you have here your 10% percentile, your 90% percentile. You can look at your statistics, which gives you a mean, a minimum, a maximum, standard deviation, variance, covariance, and then your different percentiles. So depending on how much confidence you want in your results, this is it. Quickly, again, we have here a larger model, which I go through 10 time steps, okay? Where we look at all these different elements: sedimentation, degradation, advection, input, output, sedimentation. And I go through 10 time steps in first order relations here. And so for each time you can see it's changing, different scenarios, so different concentrations, different likelihoods. And even with my inputs, sorry. So I have means for each input, sedimentation, mean, and then a distribution associated with that. Distribution associated with this. So it's not just a mean for each of these different actions. It's a distribution.
Can you show where the formula is sitting for the rate?
Mm-hmm.
That table?
The formula. I just took a single rate for each. It's very simplified. It's just saying this much at each time step, this much will dissolve, this much will leave the system, this much. But then there's an uncertainty around that. So I'd say, yeah, 40.
How do you define the uncertainty? It's the first time that you have an uncertainty. How do you define it?
Define the uncertainty. It can be subjective. As I said, uncertainty sometimes is subjective, and how confident you are of the data you have.
So this is only a number, it's a numerical, or it is a function of your data?
Well, here I took a mean. I thought, okay, let's say it's 40%. And there's a handout as well before from where I look at, Quick et al. Has a list of potential ranges and sedimentation, dissolution. And I just took random values from there and then applied a 20% uncertainty around this. So I have a mean and 20% uncertainty. And so here, so I had a mean, and then I applied 20% uncertainty, so to spread it out, and a normal distribution. And so then this is sampling from this each time in a different way. Until, so after 10 time steps, you say your water concentration and your sedimentation concentration. I'm going to look at those two now, quickly. here's water. So after 10 time steps, this is the range of water concentration. So I'm not sure, I think of nanograms per meter cubed. So there's a 98% confidence it will be between 4 and 11 nanograms per meter cubed. There's a 50% confidence it will be between 6 and let's say 7.8. So this is your confidence interval. This is the same data represented in a histogram. You can see the uncertainty and the variability associated with that. And then you have the raw data. So, again, I'm sorry that wasn't more interactive. But I hope you can see how you visualize data and how this can show, you can see the results. It's not just a single value. There's uncertainty associated with it. There's variability. If we look here, so I'm just going, well, actually, I'm going to do one more thing, okay? I'm going to look at these. I'm going to put this. Look at this as an input. I'm going to look at this as an input. And I'm going to look at this as an input. Oh, no. So, I want to look at the influence of things. So I want to pick the influence. I'm going to look at the influence of advection, sedimentation, input. So each, yeah. And you can see the influence of the different inputs. So the input is a single value, so there's no influence on the final result. It doesn't influence, it doesn't change. The sedimentation has a large influence on the final concentration. Advection, so leaving the system, has a reasonable influence. As I don't know what I call that. That next element has another influence. But your outputs. So I'm just going to... So here, each one of these, so each iteration. So we did that 1,000 times. So one value, at the end of one scenario, it was here. Another scenario, this was a value. Another scenario, this was a value. Another scenario, this was a value. And then it shows you the spread of all the different results from the different scenarios. Okay. Okay, I think it's tea time now. I can't talk anymore. I'm getting more confused. And yeah, you can ask me any questions. I feel I owe you a bit more explanation, so I'm free for lunch, for tea. I'm going to say you can probably email me, possibly, if I can send my...
I think so. If I have about 2 minutes just to wrap up, I think this is a common theme that I like to pursue in here, is that it's not going to be the only school of modeling that we do. Hopefully, if we manage to get our money and support from the commission and so on, we'll be able to run this school on a regular basis, at least once a year. And in this case, well, we'll be able to improve because, as you say, while you're here to learn from us, we are also here to learn from you because the interaction and so on, it is certainly something new and we'll smooth things out. And so what I really hope is that we should keep in touch. This group of people, I hope we all keep in touch and we share email. And if you have any questions, just ask, and we'll help. And we don't feel as if you are imposing on us, because we also learn from you about how to best communicate all our idea and get the community running. I hope you share that too. So,
definitely, yeah.
So on this note, let us go for coffee, and we'll see how it goes.